Today we're going to be doing lesson 3.1, which is on graphing relationships. In this lesson, we're going to introduce two new vocabulary words, continuous graph and discrete graph. Graphs can be used to illustrate many different situations. For example, trends shown on a cardiograph can help a doctor see how the patient's heart is functioning. To relate a graph to a given situation, use keywords in the description. So we're going to be looking at different situations and figuring out how the two variables relate to each other. So we're going to start with example 1. Okay. Example 1 says the air temperature was constant for several hours at the beginning of the day, then rose steadily for several hours. It stayed the same temperature for most of the day before dropping sharply at sundown. Choose the graph that best describes this situation. So here we're comparing time and temperature in all our graphs. So some keywords in our situation was the air temperature was constant for several hours. Constant means it's going to be straight. It's going to be horizontal. Okay, constant means it's going to be horizontal for a little bit of time. It's not changing at all. It's not increasing or decreasing, so it's just going to be flat. So it started at a constant, so at the beginning of the day. Then rose steadily for several hours. Rising, okay, means it's going to increase, and steadily means it's going to increase at a constant rate. So it's going to be a straight line, but it's going to be going up. So rose steadily means it's slanting upward. Okay. It stayed the same temperature for the most of the day. So stayed the same is our next keyword. So staying the same, again, same thing as constant, so that's going to be horizontal. Then it dropped sharply at sundown. So then we're going to have a quick decrease or slant downwards. So we need to find a graph that represents all of this. So starting constant, graph A and B start off constant, C is increasing, so C would not work. Okay, so we have starting off constant rate. Then rose steadily, so slanting upwards, so we're constant going up, constant going up. So graph A and B still work. Then it stayed the same, so we're constant up. This looks like it kind of turns downwards, so graph A doesn't look like it's going to fit. Graph B, constant, increase, constant, and then we have that drop at the end, at sundown. So graph A doesn't work. So graph B would be correct for this situation. Okay, so here we have the horizontal, slanting upwards, horizontal, slanting downward. So the correct graph in this situation is B. There is a check it out problem for you to try. It relates to these three graphs again. So I'm going to pause or give you a second to answer this question. So you can pause the video, resume it when you're ready to check your answer. So it says the air temperature increased steadily for several hours and then remained constant. At the end of the day, the temperature increased slightly again before dropping slightly. Choose the graph above that represents the situation. So here, increased steadily. Okay, so that's going to go upwards. Then remained constant. At the end of the day, there was an increase again, so increased slightly again before dropping sharply. So here we have a constant increase. So we need an increase, then constant, increased again, and then drop sharply. So here, the correct answer for our check it out would be graph C. Now we're going to look at example 2. So it says, as seen in example 1, some graphs are connected lines or curves called continuous graphs. Some graphs are only distinct points. These are called discrete graphs. So in example 1, we looked at continuous graphs because it's a continuous line or curve. Now we're going to look at an example where there's a discrete graph. So there's only going to be certain points on the graph, like this example right here. So the graph on theme park attendance is an example of a discrete graph. It consists of distinct points because each year is distinct and people are counted in whole numbers only. The values between the whole numbers are not included since they have no meaning for the situation. So they're only collecting data each year, okay? And that tells us how many total people. You can't do a year and a half because they want to do the full year here, so that's why it's discrete. So for example 2a, it says sketch a graph for each situation. Tell whether the graph is continuous, okay, that would be a continuous curve, or discrete, where we have individual points or distinct points. So A, it says Simon is selling candles to raise money for the school dance. For each candle he sells, the school will get $2.50. He has 10 candles that he can sell. So here, okay, if you want, you can create a table to help you with this. So for one candle sold, we know he's going to get $2.50. Okay, so 5 is here, 10, 15, 20, 25. So one candle is $2.50, so that would be right here. 0 candles, $0. Okay, 2 candles would be $5. 3 candles, $7.50. 4 candles, $10. 5 candles is $12.50, so about right here. 6 candles, $15. 7 candles, $17.50. 8 candles, $20. 9 candles, $22.50, and then 10 candles would be $25. So here we're relating the number of candles sold to the amount earned. Now you can't sell a part of a candle here. You can't sell 3.5 candles. They have to be sold in whole amounts. So the amount earned, the y-axis, increases by $2.50 for each candle Simon sells. Okay, this is the x-axis. Since Simon can only sell whole number of candles, the graph is 11 distinct points. Okay, so we have different points on our graph. And that means we are going to have a discrete graph. Okay, remember, discrete graph has those distinct points. And that's exactly what we have in this situation. We have distinct points. So now we're going to look at part B. Okay, so we have heart rate is being monitored while she exercises on a treadmill. While walking, her heart rate remains the same. As she increases her pace, her heart rate rises at a steady rate. When she begins to run, her heart rate increases more rapidly, then remains high while she runs. As she decreases her pace, her heart rate slows down and returns to her normal rate. So there's a lot going on in this situation. We're dealing with time and heart rate. Now, heart rate is going to be continuous because it's going to keep on going throughout the entire situation. So, first, okay, her heart rate remains the same. So this is going to be constant. Okay, so we're going to have a horizontal line. Okay. Then, as she increases her pace, her heart rate rises at a steady rate. So that's going to be an increase. When she begins to run, her heart rate increases more rapidly. So then her heart rate is going to go up even quicker. Then remains high. So that means that's going to be a constant once we get to that really high point. And then as she decreases her rate, her heart rate slows down and returns to her normal heart rate. So it's going to go slow down, and then it's going to get back to where we started. Okay. So there's a lot going on here. Okay. So first, our heart rate, it's starting. Okay. It stays constant. Then it increases at a constant rate. So something like this. But then it increases more rapidly, so then it's going to get steeper. Okay, so it's steeper than before. Then it remains high, so we get constant again. It slows down, okay, until we get back to what we started with. So your graph would look something like this. Now your steepness of your increases and decreases might be a little bit different, and they might vary, but that's okay as long as you're showing that this first increase is different than this higher increase because it's increasing more rapidly. There are 2 check it out problems for you to do. So you're going to sketch the graph for each situation and then tell whether the graph is continuous or discrete. So go ahead, take a moment, pause the video, and try these 2 on your own. So for A, it says Jamie is taking an 8-week keyboarding class. At the end of each week, she takes a test to find the number of words she can type per minute. She improves each week. So each week, she has the number of words she can type per minute. So words she can type per minute. She's improving each week. Okay, so we're only collecting data at the end of each week. So first week, she might be here. Second week, she's increasing. Third week, she continues to increase. Fourth week, continues to increase again. Fifth week, sixth week, seventh week, and then eighth week. Kind of ran out of room on my graph, but it will look something like that. Okay, this is going to be a discrete graph because we are only collecting data at the end of each week. Okay, so yours might increase a little bit more than mine or a little bit slower, but it should look something like this. You should have those 8 weeks graphed on your coordinate plane. B, it says Henry begins to drain a water tank by opening a valve. Then he opens another valve. Then he closes the first valve. He leaves the second valve open until the tank is empty. Okay, so we open a valve, open another valve, close the first valve, then he leaves the second valve open until the tank is empty. Okay, so we have the time and the water level. So here, our water level is going to start all the way at the top because it's full. We open one valve, okay, so that means it's going to decrease at a steady rate, okay, for a period of time, so it's going to decrease. Then we open the second valve, so that means 2 valves are open, so water is coming out pretty quick. So we're going to decrease a little bit quicker. Then close the first valve, and then we only have 1 valve open again. So it's going to kind of decrease at the same slope as the first one until it's empty. So it'll look something like this. So it has a decrease, a quicker decrease, then back to a steady increase that we started with until the water level is empty. Now we're going to look at example 3. Okay. When sketching or interpreting a graph, pay close attention to the labels on each axis. Both graphs below show a relationship about a child going down a slide. Graph A represents the child's distance from the ground over time. So we have time is increasing, and then the distance from the ground. So you're starting at the slide, you're going down, and then you kind of level off a little bit, and then down again. So it's kind of a curvy slide. Then graph B represents the child's speed over time. So we have time increasing and then speed. So you kind of start off slow, then you pick up, and then you slow down when you get to the bottom of the slide. Okay? So in example 3, we're going to be writing situations for graphs. So there's many different possible situations or scenarios that you can come up with for these examples, so you can really get creative sometimes. So here it says, write a possible situation for the given graph. So here on this x-axis, we have time. Okay, so we're starting at 0 time and then we're increasing. Y-axis is water level. So no water level increases, increases, increases as we go up. So now we're going to analyze each section over time and the water level. So here we start off at 0 time. Water level is increasing. Then it kind of levels off, it remains constant, and then it drops suddenly. So it's increasing steadily, remains unchanged, and then decreases steadily. Okay? So here a possible situation. A watering can is filled with water. It sits for a while until some flowers are planted. The water is emptied on top of the planted flowers. Okay, so you're filling it with water, kind of putting it to the side while you garden, so it's just sitting there as time passes, and then you water your flowers, so it decreases. There is a check it out problem for you to try. So it says write a possible situation for the given graph. So go ahead, take a moment, pause the video, and try this one on your own. Again, there could be many different possible answers for this problem. So on the x-axis, we have students, okay, so number of students, and then pizzas bought. So here, okay, we might have 1 student, 1 pizza, 2 students, 1 pizza, 3 students, 1 pizza, 4 students, 1 pizza, okay. I don't know that this is 1 pizza, but I'm just assuming, okay. And then we increase to 2 pizzas maybe for 5 students, 2 pizzas for 6, 2 pizzas for 7, 2 pizzas for 8 students. So here, a possible situation could be when the number of students reaches a certain point, the number of pizzas bought increases. So the more students you have, the more pizzas you need to buy. But 1 pizza might be able to serve 4 people. So 1 pizza serving 4 people, but then when you get to 5, you're going to have to buy an extra one. Okay? And then 8 people can still have 2 pizzas. So when the number of students reaches a certain point, the number of pizzas bought increases.